Hey everybody, Dave Lindbergh in Hong Kong with another episode of THD Podcast. Today, we have a couple gentlemen joining us from Austin, Texas to talk about low power edge processing, a company called Ambiq from Austin. And they're going to tell us all about their edge processing chips and how it all comes together. And if I've said that properly, we'll get checked on me right away. But before we get into that, let's not forget about our sponsor. As always, Barry Vogel's the president of the ALTI Association, the Audio and Loudspeaker Technologies International. So during these tough COVID times, if you can't get out to network, we encourage people to check those guys out. We'll put their contact information up here, right there, so that you can reach out to them and see what getting involved in ALTI and how it could help you with your audio business. So without delay, we have Simon back in the room. How are you doing this morning, Simon?
Really good, Dave. Good to see you again.
All right. And yeah, joining us from Texas, we have Scott Hanson and Roger Serwy. How are you guys doing this morning or this afternoon for you guys?
Doing well. It's been a long day, but we're happy to here to talk to you.
All right. So yeah, maybe let's just start with a brief introduction of yourself. I know that Ambiq's been around since 2010. I think the company, the name comes from Ambient IQ. Is that correct? Is that
wonderful. Good guess. Yeah, that's right. Yeah. So the company was founded in 2010 to put chips everywhere. And that's about putting intelligence in everything, right? Ambient IQ, ambient intelligence. So from the start, it's been about, I want to put chips in clothing. I want to put it in the pavement that we walk on, in the walls in our homes, absolutely everywhere. And we'll tell you more about what that means, what that entails, et cetera.
Okay. Roger?
Yes, my name is Roger Serwy. I have a PhD in electrical and computer engineering from the University of Illinois with a focus in voice and signal processing. Prior to joining Ambiq, I developed speaker protection and battery brownout prevention systems while at Cirrus Logic. I also implemented natural language processing and image segmentation algorithms while I was consulting with Endpoint. At Ambiq, my role is to help put audio everywhere by creating low complexity and high fidelity audio processing capabilities.
All right, very good. So how do we want to do this? Do we want to maybe walk into a presentation and have some talking points, make it easy for our viewers?
Yeah, why don't we jump into the presentation, and you guys stop me along the way with any questions. Let's make this interactive.
Yeah, for sure.
We were founded in 2010 to put chips everywhere, and putting chips everywhere means you got to be energy efficient, right? So we build the world's most energy efficient chips. And as we'll show later, these are complete solution chips. These are chips that have radios, they have microcontrollers, they have analog to digital converters, all sorts of other interesting peripherals, neural network accelerators increasingly. So the thing that makes us unique is that we have our so-called SPOT platform. I'll explain more about that later, but we have this proprietary circuit platform. It allows us to build circuits with far less energy than anything else out there. And I'll explain a bit more about that. But that's allowed us to grow very quickly. I'll give some specifics later, but revenue is doubling every year for a long time now, or more than doubling. We have unit volume that has now exceeded well over 100 million units. And we're looking to aggressively expand this so-called SPOT platform to a variety of different markets. And one of the key technology enablers under that is going to be enabling endpoint AI, so-called endpoint AI. And as I'll talk about later, inference is a piece of that, but it's the full signal chain that goes with it that's really critical. And Ambiq is strong because we can put low power in every single piece along that way. I'll talk more about that here shortly.
Okay.
So the company is 10 years old. We came out of the University of Michigan here in the US. And there we were building devices that would be implanted in the human body, in your eye, in your heart, wherever. They would be deployed on a battlefield. And the idea was, I want to run on something that's a cubic millimeter volume. So in the upper left-hand corner there, you can see a solution that's got a solar cell on top. The middle slice there is actually a microprocessor with sensors and some other things. And the bottom slice is a battery. And if you were to zoom out, what you see is that's sitting on top of a penny, a US penny, and there's Abraham Lincoln just above there. Right. So these things are tiny. We got to the point where we said, you know what, the chip portion of this is commercializable. We had a lot of a lot of companies coming and saying, I want this, I want energy efficient chips. So we started Ambiq in 2010, and we started with a timing chip, which is maybe not the most obvious first product for a company that wants to take on intelligence everywhere, but it was one that captured our core technology value, and we got it out there to millions of smart credit cards and utility meters and all sorts of interesting products. So then we, from there, went on to build microprocessors. We've got a series of microcontrollers and wireless SoCs called Apollo. So it's branded as Apollo. We've got from Apollo on up to Apollo 4 at this point. And we've shipped somewhere north of 100 million parts. That number's growing by many millions per month and even per week. So we're shipping a lot of volume. And I'll talk about some of the markets here in a second. But it's a set of products that is supported by a pretty broad range of people all over the world. So we do our core spot engineering here in Austin, Texas, but we have engineering and operations and sales support and everything else all over the world: Japan, China, Taiwan, Singapore, Poland. So we're very much a global organization.
How low power is low power? So right back at the beginning, the previous slide, you had some RTCs to begin with, and then an MCU. How low
so it
power?
depends on the product. It depends on the product. The RTC is down in the, call it 15 nanoamp range for everything. And so where that was really compelling was in smart credit cards, where they wanted to add a one-time password token generator inside the card. And you need that card needs to last for 3 years at a time on a paper-thin battery. And so they had nanowatts, hundreds of nanowatts available. So what we delivered was really compelling in say the wearable space. So we're in a lot of different wearables that I'll talk more about later, but there, your power budget is more like milliwatts. And so we talk about microamps per megahertz of processing speed. And we're setting records across the board in all those areas.
Is there a point? So the one you just mentioned was 15 nanoamps or nanowatts.
Nanoamps. Yeah, nanoamps, and that would be at 1.8 volts. So, call it under 30 nanowatts.
Is there a level at which that's just the leakage of electrical energy into the surrounding spaces? I mean,
we're right on the boundary of that. So that's where we said, okay, we proved what's possible. Now let's start to build up more capability. So, a timing chip only can do so much. Then we said, well, let's add memory and let's add a microprocessor and a radio and all that stuff. So you're getting to self-discharge of the battery at that point.
Yeah.
Okay.
So the core technology behind this is what we call our SPOT platform, Subthreshold Power Optimized Technology. And we like to say that we're solving fundamental physics problems. And that's because, in a normal circuit, you represent digital values with zeros and ones. And, a 0 is 0 volts and a 1 might be something like 1.2 volts. In subthreshold operation, which is what's central to our SPOT platform, you're representing a 0 with that same 0 volts, but maybe the 1 is 0.3 volts or thereabouts. And, nominally that sounds simple. I reduce the voltage, and voltage or energy is voltage squared, right? So you get, in this example, from going from 1.2 volts to 0.3 volts, I get a 16x energy reduction. Turns out it's not that simple, right? I mean, transistors, if you go back to your circuits 101 class, transistors are taught as either on or off, right? And to turn a transistor on, you have to exceed the threshold voltage. In subthreshold, we're never quite exceeding that threshold voltage. We're never turning the transistor on. So we're using different degrees of off transistors to drive our circuits. So a lot of challenges associated with that. One of the most significant of which is that we're exponentially sensitive to changes in process parameters, to changes in temperature, to changes in voltage. So we have to completely tear down the way chips are designed and rebuild it from the ground up. So that means digital circuits, that means analog circuits, it means memories. And over time, what we've done is we've proven that, hey, in fact, we can build a complete platform that is manufacturable. As I said, we've shipped it over more than 100 million units at this point. We've got a bunch of patents that protect it. It's a mix of digital techniques, analog techniques, system techniques, production test techniques, and they all come together in what we call our SPOT platform. Many of them patented, many of them are treated as trade secrets. A lot of it is captured in the form of production proven IP that we can reuse from design to design. So this is a technology that's very much a platform. And the upshot is I can design pretty much everything I want anything I want with lower power. So whether it's a ARM-based MCU, whether it's some kind of PDM to PCM converter, whether it's a vector DSP that is for accelerating conventional DSP and inference operations, whether it's something analog based. So we have a big analog team that's focused on making the world's lowest power analog. So we've got a really broad set of capabilities with this. And so the challenge as a small company is, what do we focus on, right? I mean, which challenge do we want to go after? And I'll talk more about some of the markets we've chosen to go after initially.
This subthreshold, is that a particularly unique concept, or has it been around for a while and finally you guys figured out how to make use of it?
So it's one that's been around since, call it the late 70s in concept. The wristwatch people went and really investigated this. There was a lot of academic work initially. In fact, a lot of the original academic work was, hey, I want to know when the transistor fails. We teach that it's on or it's off, but in fact, we know the transistor is really just an analog device itself, right? It has the whole spectrum of 0 to 1. And so a lot of the early work was looking at the limits of a transistor. And there was a lot of interesting work that showed that, hey, you can make a transistor work down to a couple tens of millivolts, depending on what the temperature is. And then that led to work on, well, should you operate down there? And then, okay, if you should operate down there, is it possible to make it manufacturable? So there was some limited, let's call it commercial deployment in the wristwatch sector a long time ago. There was a resurgence in research in the early 2000s. The lab that I was part of out of the University of Michigan was among the chief instigators of that new surge in interest. And then we founded Ambiq shortly after that. So if you look across the board, I'm going to say that the vast majority of companies are staying as far away from this as they can. It's hard. It's just really hard to do. And
right.
I think they'd mostly rather let the foundries do the work for them, right? I mean, TSMC is a fantastic engineering organization. Just let them develop the next node and the next node and the next node, and then you can jump and get better energy efficiency that way. We've chosen to break away from that. We see a big opportunity. We have a lot of customers screaming at us. So we've said, okay, it's worth fighting those challenges.
Interesting. So like if temperature is so volatile for you, is there like custom packaging that you guys need on your ICs?
No, so we make we make it a point to use completely standard packaging and completely standard manufacturing processes.
Okay.
So, for example, TSMC is our big manufacturing partner, and we use completely standard TSMC manufacturing flows. We work with a number of different vendors in Taiwan for testing and for packaging, and we use completely standard packaging. So, from the outside, it should be indistinguishable, our chip, from what a competitor offers. It just magically will consume less power than the thing that you're buying off the shelf today. And if you look at our data sheet, you go, yeah, I mean, I see these features. I see a microcontroller, I see SRAM, I see all this stuff on everybody else's data sheet. There's a big difference though when you get to the electrical table, right? And you go, oh my gosh, it's consuming a lot less power than what's there. So hopefully we make that easy. But we do, if I was to, lift up the lid on this thing and show you what's really going on inside, you'll see a lot of, for example, adaptation across temperature. So the latest generation in 7 nanometer PC processors and phone processors do a lot of adaptation across workloads and temperatures, et cetera. We're doing many of the same types of things, but for different reasons and with different sensitivities. So, we're adapting all kinds of internal characteristics based on temperature, based on the process corner. We're doing a lot of careful voltage regulation. You get a battery voltage that comes in at 4 volts or maybe 3 volts or maybe there's a system around at 1.8 volts. You still have to convert that down to something usable deep in the subthreshold and near threshold domain. So we've got a lot of expertise in doing all that stuff.
Okay.
So we've captured this spot technology in a wide variety of products, and I'll show you a portion of it. I've blocked out a piece of it here for NDA reasons or for confidentiality reasons. But our main volume shippers today are what we call our Apollo family. This is a set of ARM-based MCUs. To date, the launched products are all Cortex M4-based devices. You'll see, of course, different products. If I was to lift up the lid on that NDA only section, you'd see some non-M4 cores there. But to date, we've had Cortex M4s, we have Bluetooth radio, we have all sorts of any peripheral you want, ADC, USB, SDIO, all sorts of interesting things, and just with extremely low power. So for most of our customers, the thing they care most about is how much energy am I using, on average in a system that's doing real work, right? The 15 nanoamp example we gave earlier for the RTC, that's a very corner case. Most customers, they want to run maybe 10, 20, 30, 50 megahertz average average processor usage. And so what they care more about is, well, how much power do I consume when I'm actually active, and can I efficiently duty cycle in and out of these modes? We're just really good at that. And a lot of that is the subthreshold stuff that I talked about earlier, and near threshold operation. A lot of it is, as I like to say, we're a group of picojoule fanatics, and we have to make sure that everything we design is designed with energy in mind. So the way we do our clocking, the way we manage our buses, the way we do everything internally is very much energy driven. So, so what you see is that these are very, very efficient to use. The Apollo 4 product is our most recent one. I'll talk more about that in a moment, but I like to say a lot that our roadmap moves up and to the right. So that means with every passing year, we're adding more features, we're getting faster, we're getting more energy efficient, we're enabling new capabilities. We got a lot of customers today, for example, that are running inference on a Cortex M4. And is the Cortex M4 the best option for running inference or for running audio pre-processing? Absolutely not. But this is a really good energy efficient solution. And for most of these people, it's about full signal chain. Inference is maybe one small piece of the pie. You've got to get the data on chip. You've got to send the data off chip via a radio. And what Apollo 4 is a really outstanding solution for all that.
So I was curious about one thing. Just curious about one thing, Scott. So when a company, whoever comes along, they want to build a chip, something like this, that has got MCU, RAM, flash, Bluetooth, USB. Do they develop the chip by sort of stitching together IP blocks from other vendors and then ask a chip maker to produce that? Does it work something like that? So what I mean
you're
to say
asking
is,
to the chip. Go ahead.
So let's say Microchip want to produce this chip. They don't start from scratch and develop a Bluetooth low energy block on their silicon. They would buy that IP from somebody.
It's a mix, right? I mean, so we of course make our chips, and we do a mix of licensing certain things that are off the shelf, and then hyper optimizing things, other things. So as an example, a USB interface is not generally an opportunity for innovation. It's a thing that has to be there. It's a checkbox, but nobody cares about how good or bad it is. It just has to work, right? So that's a great candidate for licensing. Something like like the M4 itself, I have to license that from ARM, but I want to implement it using my own spot technology, right? I want everything below the so-called RTL level I want to do myself. So if you were to break open an Apollo chip, you'd see a real mix of the stuff that really matters from an energy standpoint is in-house developed or is absolutely spot enabled. The stuff that maybe doesn't matter from our customer standpoint is just a checkbox, maybe licensed.
Okay. That's actually where I was getting to with that point. So the level of design that you have to go through for your chips would be a lot deeper than some other chip makers who are using kind of standard technologies, let's say. Is that fair to say?
Yeah, I mean, in a sense, although I'll say that our design methodology has been well honed over the years. And so you give me a new IP block and I can integrate it and make it spot enabled very, very quickly. Right? Okay. And so that's a core part of our IP. Our methodology is a core part of Ambiq's IP. So we can go from product to product without worrying too much. I mean, this is actually one of the concerns I have about some of the alternative low power approaches are things like, let's use asynchronous circuits, right? Asynchronous circuits, there's no, you throw away the clock and everything is kind of self-timed. It's very scary. It's really cool academically, but it's very difficult to make work in practice. It's difficult to take that technology and apply it to some completely new IP. So if you say, hey, Scott, it's great that you have an M4, but you need to have a vector DSP that can run inference and DSP. If I'm doing asynchronous, I can't do it like this. With Subthreshold, we can. We have a completely synchronous approach. We use standard CAD flow. We're using standard manufacturing flow. So it's a pretty nice and flexible technology platform.
Okay. And say for this Apollo 4, what are we talking about in terms of power consumption again? Is there any typical figure?
Yeah, it depends on the workload. 4 microamp per megahertz is kind of the key number I'll throw at you. And that's at a 3.3 volt equivalent. So, call that, what is that, 14 microwatts per megahertz zone, or 15 microwatts per megahertz. And that, unfortunately, over time, that's for a long time, that's been a really good indicator of energy efficiency, because a lot of the work was done by the core. But this is a chip that has a GPU. It has all kinds of peripherals that have intelligent capabilities attached to them. It has a lot of stuff that just doesn't even involve the MCU. So I give you that as a reference point for saying how efficient we are, and you can assume that all the other peripherals are equally efficient.
Sure. How much does it cost?
Oh boy, that's not a question I'm well suited to answer. I don't know that we publish.
Can you put it into an order of magnitude range then?
Yeah, I mean, we're in the let's say the Apollo family overall. If you look at Apollo 2, 3, 4, it's in the N dollars range, sub $10 range, right. And we have parts that can get well below $5. So single digit dollars is where we are, and of course for high volume stuff we can go pretty aggressively low. I mean, we're being used in very high volume products today that are from the top brands, and let's just say that they're not shy about asking for good pricing. So
fantastic.
So we have a lot of exciting things coming, and what I would propose is let's come back 6 months from now and let's talk about some new launches that are in the works, and let's get into some of the more exciting stuff. But for now, I want to talk about Apollo 4. It's out there today. We have customers shipping it, and it's interesting from a voice and audio standpoint. While not designed from the ground up as a explicitly voice processor, it's one that's meant to support customers who do graphics and voice and security and all sorts of other things. So a couple of things to draw your attention to. We've got a roughly 200 megahertz processor, 192 megahertz processor that's Cortex M4. We have a low power audio subsystem that includes support for analog microphones. So this is in Apollo 3, we support digital mics. On Apollo 4, we support both digital and analog. The analog mic interface is hyper optimized for power, so it's meant to be very much an always on front end. These analog mics consume almost no power. If you get into the hearing aid space and you start using some of these very low power analog mics, you can get down to 10 to 20 microwatt type power consumption numbers. You pair that with an ADC, it's got to be in that same range. Otherwise, you're blowing your power budget out of the water. So that's very much what that analog mic interface is about enabling here. It wasn't something we could find off the shelf, and so we went out and designed that. And then we also have support for up to 8 digital microphones. So you can start to get into some far field processing. You can start to do it's also a high dynamic range interface, so we can get into some interesting, let's say, voice call type use cases. Imagine we've got a lot of customers in this type space, wearable space, that want to add voice control. So I'm talking to my watch, but also maybe phone call extension. So I'm handling a phone call that's relayed through my phone, and so this thing has to be very much voice capable at this point, and Apollo 4 is ready to support that. And then the last thing I'll just add is it's got a huge memory. Okay, so if you go talk to the software people, there's never enough memory, right? They always want more, and 100% of our customers are already maxing this out, and so you can expect that there are new products that will be announced imminently that have even more memory out.
I think there was a few companies launching the edge processors that kind of overlooked the ADC implication of what we call the system power consumption. So they went to market, and then people go, well, we want to use an analog mic. Now what do we do? And then it was kind of like, one of those moments where, okay, we go back and need to add it into the low power architecture. So is that something similar that happened for you guys?
Yeah, and I would say that originally when we added a PDM interface, it was something we added opportunistically. We heard some chatter among our customers that we might want to add some voice, and frankly, it took them a long time to get there. And so it was okay to use PDM, but yeah, we realized pretty quickly that a PDM interface is where you're essentially splitting the ADC into 2 pieces, and you're letting some of it be on the microphone and some of it be on the chip. And we said, well, wait a second, we're just really good chip designers. Let's pull it all on chip and do that. And frankly, a company like Infineon is great at doing the MEMS, they're of course a great circuits company too, but let them do the MEMS. Let us do this low power circuit thing that we do really well, and I think it's a nice kind of scenario. I'll talk more about this at the very end of the presentation, but we have some longer term work focused on the ADC side of things, and we're doing some really exciting work on low power ADCs. It's an area where I think that the state of the art is well above the floor of what's possible, and we're really interested in getting it down to that power floor.
Okay.
And if you're developing for this Apollo 4, what sort of tool chain are you using?
So we use completely standard tool chain. So if you want to develop, for example, in Kyle complete tool flow, you can do that. So you can use the Kyle IDE and the ARM compiler. IAR is also supported. And then if you're an engineer that likes to use GCC, GDB, just kind of the command line tools, we can support that as well.
Oh, fantastic. Yeah.
And I should mention too that, this, over time, our chips have become so complex that you can't just give a chip. You have to give a complete software stack. So we like to call ourselves a solution vendor. So you buy Apollo 4 and it's going to come with a Bluetooth stack. It's going to come with a whole graphics stack so that you can drive your display, and now increasingly all the audio stack as well.
Right.
Okay, so I've blurred out a lot of this, but the Spot today is being used in a wide variety of use cases at a wide variety of customers. So we've got tons of wearables using this. If you look at teardowns, you can see Garmin, Fitbit, Oppo, Huawei all using us, and there's a bunch more that I can't name, but you can say that there's representative types of devices up there: smartwatches, analog watches, fitness bands, anything that wants to last for days, weeks, months, years on a battery. They want to use us. We're being used in all sorts of interesting credit cards. We're being used in animal trackers. We're being used in utility meters. So really, the volume thus far has been driven in large part by wearables, but we're very much an Internet of Things company, and we've got a really broad scope. And what's interesting for your audience is we see voice being used, of course, in wearables and in hearables at a lot of our customers, but we're also seeing it expand all sorts of things. So whether it's industrial machine health monitoring or smart home devices that you want to talk to, we're seeing voice everywhere, and we're enabling that today.
Mm-hmm.
So we're interested today in, well, what happens if it's not just connected devices, but if these devices are truly intelligent? And over time, we've seen our customers add more and more intelligence, but we're now getting to a tipping point where you can run maybe a pretty serious neural network on these devices. Maybe you can run a couple gigamax per second. You can put a pretty sizable neural network on these devices. What's possible? Well, we want to shrink Alexa, the Amazon Echo, down to a sticker that can go in every room in your house and last for years in a battery. We want to make your wearable device a doctor, not just something that's reporting heart rate and the basics, but it should be a doctor that tells you, what your health is, what might be coming on, and what you can do to actually make yourself healthier. So think about preventative healthcare rather than reactive healthcare. And certainly voice is central to all of this. And that's a big focus of what we're doing right now, is we're trying to enable voice everywhere, not just intelligence everywhere, but voice in particular. And there's a couple markets that are of interest and where we have traction. There's the gaming controller market. We're seeing smartwatches and smart bands all deploy voice. And that's out there today, and we're seeing them step up with every generation of the functionality. A lot of remote control engagements that we have. So, we're seeing TVs, of course, embed far field voice control inside them, but people still have a remote control. It's kind of a little remote microphone that gets placed around the room somewhere. A lot of headphone use cases. And there, the audio use case is not just about voice. I want to obviously interact with my headphone, but I also want to have interesting transparency modes. This is an area you guys, I'm sure, know quite a bit about, but I want to have interesting transparency modes. I want to overlay that on top of best-in-class noise cancellation. And there's a big processing burden there that has to be done, and that's something that Ambiq is really well tuned to take on. And then finally, I'm actually really excited about the non-consumer stuff too. So I want to go put smart sensors around the home, around the building, or on the factory floor for security reasons, for machine health monitoring reasons, et cetera. So really some interesting voice opportunities and broader audio opportunities everywhere. And I'll talk in a moment about our particular solution. It's something we call VOS, or Voice on Spot. But as I'll get into in a second, this is not about, as in the cloud, where it's just about how many teraops or how much compute power can you bring to bear. Here, it's about fitting into microwatt, megahertz, megabyte, cent kind of footprint. And specifically, if I take a look at a typical smartwatch teardown as an example, you see that if I look at the battery capacity, you're going to and you look at the battery life expectation, we're going to need anywhere from, say, 300 microwatts to 2 milliwatts average power. That's what you got to hit. And by the way, the photo I'm showing on the left is a publicly available teardown of one of our customers' products that contains Apollo 3. There's a couple different processors that maybe have anywhere from 48 to 120 megahertz max clock frequency. Of course, we're starting to push that, nudge that upwards with some of our latest products. But you've got a few megabytes of NVM, maybe a few hundred kilobytes moving to a few megabytes of SRAM. And you got to fit it all into maybe $5. Some systems are closer to $10, some are closer to $2. But your chip BOM, which includes the processor, the radio, the sensors, the PMIC, all that stuff has to fit in that BOM. So, this is not about, like I said, the data center, where it's about how many teraops, how many huge number of teraops can you compute. It's about fitting all of that into the kind of economics that work for smartwatches, right? And that's what's going to be necessary. So that's what Ambiq is very much about. It's not as sexy as saying I can fit however many teraops or however many teraops per watt is my power budget, but it's something that is real. And so we like to say that the voice everywhere problem is a full signal chain problem. So you got to do sensing, you got to do some kind of signal processing and storage on that data. Then you've got to do inference. So that's certainly a piece of the puzzle. But then there's also some other things. I've got security that I've got to run. I've got decision making. I've got some higher level OS that's running. Maybe there's some user interaction that's happening. And there's communications too. I got to get that data off chip, whether through a display or through a radio. And then the piece that a lot of people forget about is the power management. Again, as I said earlier, you got a battery voltage way up here. I've got chips that use it way down here, and I've got to deliver it efficiently. So all that's got to fit in 1 milliwatt, and increasingly it's got to fit on a single chip, right? It's not enough. You can't have a multi-chip solution because there's also volume constraints too, right? Especially in the in the TWS space. So that's what Ambiq is about.
Yeah, so it's a lot of, to me, the roadmap is kind of articulated a bit by strategic consolidation. What are you bringing inside the single IC, and at what time, based on your customer feedback? So it's kind of a tricky game to be predictive.
Absolutely, yeah.
If we bring this inside and nobody wants to pay for it, we're in big trouble, kind of situation.
Yeah, and we're getting to pull back the covers a bit on the economics of chip making. We're getting to the point where we're in really advanced nodes where the masks are really expensive. So the NRE that I'm paying to make a chip up front is really high. So you have to make one chip as flexible as possible to cater to many markets.
Yeah.
So now you're debating, well, do I include the power management circuitry on board? Do I let that be a separate ASIC? And yeah, we're having to redraw the lines constantly, and the customer's expectations for what they need out of us are being redrawn constantly too. So, if you compare the first generation Apollo to Apollo 4, they're worlds different in terms of what they've integrated.
Okay.
I was always curious about that. These type of integrated chips. You've got Bluetooth, USB. Don't like it, doesn't matter. It's there. Any one customer actually only ever uses a small subset of those peripherals. Is that right? But you have to include them all so that the chip has a broad enough applicability.
Yeah. I would say that we do see that many of our customers are using a large fraction of the peripherals. So there's high usage. And fortunately, again, because we're in advanced nodes, the burden, the cost overhead of adding another PDM interface is incrementally relatively small. So I can afford to add that there because, again, we're using 22 nanometer process nodes. So digital becomes really small. Memory ends up being the key driving cost factor. Both the number of megabytes of NVM and SRAM that we have, but also the types of memory, right? I mean, we have MRAM today on our chips, and that adds extra processing layers, so that's cost. So what you tend to see us do is we offer one chip, and then over time we'll offer a series of derivatives that are optimized for different cost points. I mean, we walk away from a lot of business today because I don't have the one chip that's optimized to sell at 50 cents, right? I've got all the full spectrum, and then I don't have that one. But the minute I do, there's going to be a whole lot more Ambiq chips being shipped every single month. So it's Important for us to, as I said earlier, to go up and to the right with the roadmap. So more integration, more, but it's also to grow out, which means have different flavors that sell for different prices and with different peripheral sets, et cetera.
Okay.
Okay, so that brings me to Voice on Spot, the product that we have. It's a complete solution that layers on top of our Apollo family. So Apollo 3 and Apollo 4. And it is a set of software that goes complete end to end. So it starts at the microphone and goes all the way to communications via BLE. You can use it in different pieces. Think of it as Lego pieces that you can slap together. And it's got everything from analog to digital conversion. I show PDM to PCM, but we also have the A to D for support analog microphones. You go through some pre-processing that can be things like beamforming, single channel noise reduction. Subsequently, we have inference on board in the form of keyword detection. We can support multi-commands, so we can do, I think our current demo shows 10 or 20 commands, but we can do 50 or 60 commands, and that number will grow ever larger too. As we build up our software solution. And then you get to the back end, there's all the security, there's the encoding, the compression, there's the BLE communications itself. And this actually hooks into the cloud. So we've got support today for both Google and Amazon cloud solutions. You can talk to Alexa, you can talk to Google Assistant, and you can get the response back. We have a really flexible partner network. So I'm showing some example logos up there of companies that we work with. Some of them are companies that you've spoken with yourself. And there's a bunch of others too. We talk to a lot of companies that say, or customers that say, I need you to support vendor X because that's my preferred software vendor. And we say, okay, no problem, we'll do that. But we've worked really closely with a lot of these vendors to micro optimize for energy. It's one bad line of code, I like to say, completely destroys a power budget or a performance budget for that matter. So we work really closely with these companies to make sure that one bad line of code doesn't make it in there.
Yeah, if people want to go back and find out about Vesper and DSP concepts, we can put the links up here for you. So
perfect.
All right, keep going.
Okay, so the kit itself is pretty fully featured. We got a lot of companies pulling down EDKs. They can buy the hardware. They can go very quickly prototype a system that's talking to Alexa or talking to Google Assistant. And we do a really good job of helping power optimize. So if you look at a typical skyline plot here, you've got most of the time being spent in so-called wake on sound mode. I call it 4 microamps. You occasionally wake up because you hear sound. Roger here is an algorithm designer, among other things, and he's designed us both high-performing and energy-efficient voice activity detector, or a series of them, in fact. And then we jump into keyword detection mode. It consumes more power, and then at some point you got to compress and transmit. So these are kind of full solution numbers. It's not even worth getting into the specific numbers because everybody's comparing apples to oranges. What I want to show you is that we really hyper optimize all these different pieces. This particular example is for Apollo 3. Apollo 4 really takes these numbers to a next level, to very, very low. It allows us to introduce analog microphones, et cetera. But this is very much a low power audio solution. Is the Cortex M4 the best audio processor you can get? Absolutely not, right? And we have some really interesting roadmap products that we could talk about another time that address that. But at a complete solution level, it's there. I mean, if you're sitting down today to design a watch and you're driving a display and you got all this other stuff and you got heart rate, and then you want to add a voice function, we give it to you like that, right? Here's the software that does it, activate this peripheral and you're ready to go. And that's where we're getting a lot of activity. You'll see us being used in wearables for this, in headphones. We're being used in auto accessories. We're being used in remote controls. So we've got some really good initial wins. And once you get there, the customers start telling you, in Gen 2, I want you to add this and add that and add that. And so what you're going to see is a really powerful set of solutions coming in our next gen.
Very good.
The board looks like this. I don't think it's worth spending too much time on, but go to our website. You can buy this thing. You can pull it down. It's Arduino compatible, Shield format. It comes with microphones and everything you need. What's exciting, as I've said, is Apollo 4 is the next gen. We've got this whole analog mic interface. We've got some interesting software that allows it to extend its dynamic range up to 75 dB. We've got PGA on there that allows us to kind of tune the gain up and down. It's as I said earlier, capable of supporting phone calls. So you've got PDM converters on board that support up to 8 different channels. We got 120 dB dynamic range there. So you've got a pretty wide range. We can support really high fidelity audio and a whole bunch of other stuff. Briefly to say, for the more adventurous developer, sometimes you want to develop your own neural network, right? And so TensorFlow is a really interesting tool for that. We worked with Google and with SparkFun to develop this board here. It's an Apollo 3 based board, but what's most interesting is the software stack that sits above it and allows you to go train your own custom models. So that's out there today. I'll be honest with you that most of our customers are not doing this. They're using expert off-the-shelf software, and we support that. But I think in the next couple of years, we'll see a transition to in-house development.
Okay.
And then finally, I'll say that we're looking at the complete signal chain moving forward. And I'm talking about adding spot everywhere. So I want to sense and actuate, I want to infer, and I want to communicate. And Ambiq is doing really innovative work across the board. I'm not really in a position today to talk about the specifics of that work, but I'll say that I want the input and output, so the ADC and the DAC, to be 0 energy. 0 is the only acceptable number at Ambiq for power, right? On the inference side, it's the same thing. And I like to say that we offer free MIPS to our customer. Free in the sense that it's not going to burden your energy budget, right? So I'm going to give you as many MIPS as you want, as many gigamax as you want. And we've got some interesting architectures in the work to enable that. So I'm giving my customers the hardware. Now show me the really cool stuff that you can do with all that. And then finally, on the communication side, we support BLE today, but Bluetooth dual mode is something that you should expect to be coming. And there's other wireless standards that you should expect to be coming from Ambiq and at power numbers that are worthy of the Ambiq name. So we're excited about the full spectrum of innovation that's happening in Ambiq. So that brings me to the end, and I'm happy to answer any questions. And Roger's happy to answer any questions you guys might have.
Did you develop the Bluetooth hardware elements, the silicon yourselves?
So it's a mix. Yeah. It's a mix. Let's just say it's a mix of partnership with certain third parties that are experts and some work that we did internally. And a lot of the Bluetooth game is actually in the software, right? You start looking at these skyline plots and you go, why is there this enormous building there that shouldn't be there? There's a lot of power, and our software team has done a lot of work to optimize that.
Yeah. And do you think that the Bluetooth element is the primary communications channel that the chip will be using?
The answer is yeah. For most of the devices we're tackling, Bluetooth and BLE are the chosen device that or communication standard. Mm-hmm. For anything that's body worn, you're gonna tend to see that Wi-Fi is making big strides. So a lot of actually the energy budget of the radio, depending on the use case, is sitting and maintaining an idle connection. So it's not actually, clearly in a headphone, the power is in streaming audio, but in a wearable, for example, most of the power is spent just pinging the phone. I have to every 100 milliseconds, 300 milliseconds, whatever, maintain an idle connection. So Wi-Fi has gotten considerably better in that respect. And so I do think that we'll start to see more Wi-Fi. Clearly, Wi-Fi has its uses, right? I mean, where throughput matters, Wi-Fi is a big deal. Where you're communicating with a wall plug base station, like in the smart home, we expect Wi-Fi to be a big thing. So my prediction is that Wi-Fi and Bluetooth for the smart home, smart building, smart personal device kind of use cases, Wi-Fi and Bluetooth will be the predominant winners.
They coexist. I mean, they fulfill slightly different.
Yeah, absolutely. Yeah. And I think we're also seeing low power wide area network standards pop up. So NB-IoT is really interesting as a cellular, basically cellular low power standard. LoRa is another one that's of interest. So there are specific use cases there where you've got a oil pipeline sensor that's out in the middle of nowhere and it's got to communicate over a long distance and you're monitoring the sound of whatever's going on there. Yeah, there you're going to communicate over some LoRa link or over some NB-IoT.
And a slightly different one, sorry, Dave, just in terms of voice activation or recognition of commands. So Alexa, Google, they're actually very good. They work really well. But a lot of other people's products just aren't at that level. Do you think that they're getting close to being at the same standard as an Alexa or a Google? Quite a gap.
Yeah, I mean, actually, Roger, I'd be interested in your take on that because you spent a lot of time looking at the quality of these algorithms.
When it comes to doing the wake word detection, that's a statement of how good you are at turning on the system, going from a low power state, bringing the sampling system up and running, and then capturing that data and seeing if the words are there. Sometimes if you don't wake up fast enough, you can truncate some of the beginning of the wake word. So you say Alexa, but you get Lexa because it took too long to wake up. Some systems can do that. So you have to have a wake word engine that's tolerant of the turn on time. That's typically what I see with the systems that don't have good response to someone saying the wake word. Also, reverberation can be a problem. If you're in a big room and you have the microphone on the other side of the room, reverberation can reduce the performance on wake word engines dramatically.
Yep. So you have that sort of system. You have wake word, and then capture the next block of audio and send that off to the cloud to get processed. But I'm talking about giving commands directly. So you show one, okay, increase the volume. Those things not so fantastic at the moment. Do you think they're getting close to becoming really natural?
The trouble we run into with that is having speaker agnostic recognition. You have a lot more MIPS in the cloud, so you can have a lot more of processing you can apply to figure out if this person's speaking with a certain accent. You have the training data on that. Doing speaker agnostic inferencing on a low memory footprint, low MIPS budget CPU is not as robust toward the wide variety of types talkers you have.
Yeah.
Mm-hmm. Yeah, I mean, I'll say the good news is this is precisely the problem we're solving, right? I mean, you go talk to your average keyword or key phrase network developer, and they're going to say, hey, just give me more memory, give me more, gigamax per second. And that's precisely what we're doing, right? We're doing that without compromising the power budget. So I think they will get better. I'm very optimistic. I'm admittedly as a startup founder, CTO type, of course I'm optimistic, right? That's kind of our nature to be that way. But I'm optimistic that we will very soon get this solved. We're seeing some interesting performance out of some of these vendors for the 50 to 60 key phrase use case, and you can emulate NLP there. Especially if you were context aware. Like I'm in the running menu on my watch, so there's only like 10 things I could possibly ask in the running menu. So I'm going to allocate five commands of the 50 to each of the 10 actions, and you can kind of emulate that. So increase volume, raise the volume, et cetera, all end up being the same. That said, the performance of those algorithms is certainly not up to what Alexa is or what Hey Google is. I think we'll get there, and Ambiq aims to be at the forefront of all that. So again, free MIPS. We're going to have free MIPS available. Software developers, go use it as you will.
Yeah. So I think obviously there's certain brands that would be ideal customers for you, but I guess what I'm asking is are there identified third-party design houses for kind of the small to medium-sized customers that want to, enter this market, but maybe they just don't have the volume driving to be a direct customer? Do you have these guys in US, in Asia established?
So yeah, I mean, there's a bunch of different players in that space. We certainly work with a lot of different ODMs, and for fear of upsetting any of them, I'm not going to name any of the ODMs that we work with. That's something that we can talk with offline. Sure. But we talk with a lot of ODMs. They all have reference designs. Many of them with VOS. They all have reference designs with Apollo 4 and Apollo 3, and many of them now have the voice and spot stuff going. So, if you do want to go and integrate voice and spot into a wearable or some other product type, we have ODMs that we can set you up with for sure.
Okay. So we can expect a lot of the usual suspects are already lined up.
Yeah. And I guess I'll say that with the caveat that we're in a crazy global climate where the supply chain is all out of sorts. So we are certainly careful about what customers we take on these days, but believe me, our capacity is significant right now, and we're adding new customers all the time.
One of the issues currently for small to medium-sized customers, if they want to enter these new tech areas, if they don't have support regionally with their factory, they're not making any progress because they typically won't have this skill set in-house. So that's kind of the background why we're asking that.
Yeah, sure.
All right. So yeah, we'll put your contact information below and all that. If you've got Twitter and LinkedIn pages, we'll put those links below for everybody to check out. And we encourage everybody, as always, that like, subscribe, Give us your comments, give us your love, give us your hate down below. And so Scott and Roger, thanks you so much for taking the time out of your evening to join us today. We appreciate it. And we'll probably get around to an update a year from now as you guys launch what's underneath that NDA little
let's do it again soon.
Sticker.
Thank you guys for your time. It was a pleasure.
All right. See you, everybody.
Bye.